All right, we can start something completely new. We're going to start talking about Chapter 9. In Chapter 9, we talk about sequences and then series. This is a complete sidestep from all the integration techniques that you've had up to this point. We will be using them, but it's not just integral after integral after integral. That's not what we're talking about here. We're going to be talking about these two ideas called sequences and series in this chapter. And in the first section, we're going to limit it just to sequences. We'll talk about what a sequence is. I'll show you how to get terms from a sequence. Get a sequence in sequence notation from a series of from a sequence of terms. I'll also show you how to tell when a sequence will converge or diverge. Those two ideas are going to be very important for us in this chapter. Most of what we're going to be doing is testing for convergence or divergence. Whether a sequence or series goes to one number or whether it doesn't. That's in the basic sense of things. So, in section 9.1, we are going to get a very in-depth discussion of what sequences are all about. Again, I'm going to try to teach this to you because if you're like me, you didn't get a lot of exposure to this before right now. Which means that you might have seen a sequence before, but you really don't know a whole lot about them. We're going to learn a whole lot about them right now. First thing, what a sequence is. So a sequence typically denoted like this, A sub n. It's a set of terms and the set of terms is based on, well, whatever this sequence is given to you as. It's typically going to be first term, second term, third term, and we denote those as A sub 1, A sub 2, A sub 3, all the way until we get A sub n, wherever we start. N is always going to be a positive integer for us. We can't have a negative term here. So we say, hey, we have the first term, it's A sub 1. Sometimes you can do like the 0th term, A sub 0. But typically we have A sub 1, A sub 2, A sub 3, A sub 4. So n is going to be our positive integer. Also, these sequences can be denoted like this. You don't see this very often, at least not in our class. It can be given to you like this, where we say your n's going to start at a certain spot and it's going to end at a certain spot, or it doesn't end. We can denote a sequence like that. So this says, hey, here's what you're going to be working with. This is going to be some sort of notation like n plus 1 over n. Or n squared over n factorial. It's going to give you, it's not just going to be A sub n, okay? It's going to give you something there to work with. Then it says, hey, I want you to start your n at 3, or at 5, or at 1, and I want you to end at 7, or at 12, or I don't want you to end. I want you to go forever and ever and ever. And we'll talk about that. Does that make sense? If this is not shown, so if you don't have that, then n starts at 1. So if this isn't here, if not shown, n starts at 1. Now what I'd like to do is go through a couple of examples of just what sequences look like, just so we can get the habit of listing out terms, seeing what these things are actually doing. Would you guys like that? Be helpful? Because right now, are you a little bit confused on what sequences are? Okay. Some of you probably have never seen sequences before. So here we go. Here's an example. What we're going to do is we're just going to start listing out some terms for the following sequences. So here's how a sequence could look. I'm going to make it look a little like, what the heck? Just so you see that it's not that big of a deal to list out terms. They're very easy to list out terms. Okay, that right there is something that's in sequence notation. We have something that's, do you guys see how this is in terms of n? it says, hey, here's this sequence in terms of n. It says, well, where's the n going to start for us?
1.
Why is it going to start at 1 automatically?
It's not noted.
If I'm not giving you anything over here, this thing's going to start at 1. So here's how we find out the terms of our sequence. It's not hard. All it is you start wherever I tell you to start. If I don't tell you to start anywhere, you start at 1. That would mean that our first term, a sub 1, would happen when I plug in 1 for our n. So for instance, we go, okay, well, what happens when n is 1? That would be our first term. What's going to happen when n is 2? What's going to happen when n is 3? Or n is 4? Or n is 5? By the way, is this ever going to end for us? So we're just going to list out the first 5 terms just to get a feel for it. So if I want, when n is 1, what I'm going to get out of here, we're going to call this a sub 1. It's going to be my very first term. It's going to say the sequence of a, so that's this thing, when I've plugged in 1, or basically the first term of our sequence. Show of hands feel okay with the idea here. It's not hard to find out. You just got to plug in 1. So let's plug in 1. Where do we plug the 1 into again?
N.
Okay, so let's work through it. What's n plus 1 when n is 1?
2.
How about negative 1 to the second? What's that?
1.
Okay. This would be 2 to the first. How much is that?
2.
So it would be 1 times 2. So we're going to have 2 over what?
2. 1.
Perfect. Yeah, we're going to get 1 out of that. You guys okay with that so far? I'm going to erase that and put it 1, but that's where it's coming from. It's just plugging in 1 and doing a little simplification. So here's how we'd say this. The first term of our sequence, or a sub 1, is 1. How we got it was we plugged in 1 for our n. You don't have to show all this stuff. Basically, we just show first term, second term, third term. I'm just kind of denoting this so you understand what all this stuff means, okay? A sub 1 means the first term of our sequence A. N equals 1 means, well, that's how you find the first term. You plug in the 1. Does that make sense? Let's plug in the 2. So this would be our a sub 2, or our second term of our sequence. How you find the second term of our sequence is, if you start at 1, you plug in 1. If you want to find the next term, you're going to plug in what?
2.
For what?
N.
Plug in the 2. So, all right, plug in the 2. If I do 2 plus 1, notice I'm doing 2 here. 2 plus 1 is?
3.
Negative 1 to the third is?
Negative 1.
Okay, so we know negative. This is going to be negative, basically. That's all it's saying. 2 to the second is?
4.
So this would be negative 4 over
3.
Now we're plugging in 2. So the first term we got 1, the next term we got negative 4 thirds. Here's my next question to you. I want to see if you're really paying attention here, all right? First term was positive, second term was negative. Third term, what do you think that's going to be?
Positive.
How about the next one?
Negative.
How about the next one?
Positive.
How about the next one? Is it going to do that forever?
Yeah.
Yes. Because this right here, that negative 1, that doesn't change value, but it will change sign. And says, hey, plug in a number and add 1 to it. It's either going to be positive or it's going to be negative. Because we're either going to get an even number or an odd number as an exponent. Does that make sense to you? This right here gives us that alternating type of a sequence. Positive, negative, or negative, positive. My point is, do you guys see that this is going to do that forever?
Yeah.
Okay, so next term is going to be positive for sure. Let's check it. How would I find a sub 3? What would I plug in?
Can you just look at the pattern and go through it?
Say what?
Oh, never mind, you gotta do A sub 3 first.
Yeah.
But I'm saying I noticed there's a pattern there.
It's going to be positive, negative, positive, negative,
Well,
positive.
not only that, but
There's going to be a pattern for sure. Most of these things do have a pattern to them for us. So plug in the 3. 3 plus 1?
4.
Negative 1 to the fourth is
1.
positive. It's positive. I don't care if it's 1 or not. It's going to be positive 1 or negative. It's just telling you it's positive because I'm multiplying by something, right? This is going to be 8. So I'm going to have positive 8 over
4.
You guys okay with that one?
Yeah.
Let's do the fourth term. Why don't you do the fourth and the fifth terms for me, okay? try the fourth and the fifth terms for me. Let's do that. When you plug in the fourth, plug in for the fourth term. So basically when I'm looking for a sub 4, I plug in 4 to my n. I know if I plug in 4, 4 plus 1 is 5, that's an odd number, therefore I'm going to get a negative. Negative 1 to the fifth is going to be a negative term here. So this should be 16 over 5. Negative 16 over 5. Did you get the same thing?
Yes.
And lastly, for a sub 5, just plug in 5. I know my sign's going to change to, from negative to positive because I'm taking, hey, look at that. I'm taking 5 plus 1. If I plug in an odd number, it's going to add 1 to it, give me an even number. Any negative to an even number is going to become a positive. So it's positive 2 to the fifth is 32 over 6. 32 over 6 is 16 over 3. Positive 16 over 3. Okay, I really do need to show hands feel okay with that. Again, is this sequence ever going to end?
No.
No.
So we just found the first 5 terms, but notice that it doesn't end forever. You can do this forever and ever. It's always going to alternate. Positive, negative, positive. Have I explained well enough why it's alternating from positive to negative, and then negative to positive, and back and forth and back and forth? Have I explained that well enough for you? Here's my next question now. Let's look at a different sequence. Is this sequence going to alternate positive, negative, positive, negative, positive, or negative, positive, negative, positive? Is it going to do one of those things? What tells you immediately that this is going to be an alternating sign on these terms?
Negative 1 to the power.
Right there, that's it. When you see this, that's going to be alternating. For sure, because we're going to start off either with a positive or with a negative, but the next one's going to be a different number, right? Next one's going to take that negative 1 to a different consecutive number. So if we start with an even, the next one's going to be odd, the next one's going to be even, the next one's going to be odd, and then even, odd, even. And negative 1 to an even versus an odd is the difference between positive and negative. Show hands feel okay with that one. So we're going to have this idea again. Now, nextly, tell me something interesting that happens here that we didn't happen on our first sequence. Do you see why on this particular sequence I'm starting at 2?
Square root of 0.
Yeah, I mean, if I started at 1, I had to get an I. And, well, we're not talking about that in this class. We're talking about real numbers. So this would be undefined for the real number system. Does that make sense to you? So we got to start at 2 for this one. Let's go ahead. Now I want you to figure out the first 5 terms of your sequence. Go for it. First 5 terms. You don't have to do n equals 1, n equals, you don't have to show me that. You don't have to even show a sub 1, a sub 2, a sub, I'm probably going to do the a sub 1, 2, 3, 4, and 5 just so you see what they are. But you don't have to do that. All I'm asking you to do is, when you start here, well, we would start at a sub 1. We'd start at a sub 2. Then we do a sub 3, a sub 4, a sub 5, and a sub 6. Does that make sense? It will be the first term, but it's a sub 2 because that's our number to plug in. Bless you. So I want the a sub 2, a sub 3, a sub 4, a sub 5, and a sub 6 terms. Basically, we're plugging in 2, 3, 4, 5, and 6. It's not going to end. We're going to stop, but this thing doesn't end. It goes to infinity. We just have to start with a sub 2 because it says, well, wait a minute, you're starting at n equals 2. Because we listen to our terms a sub n, you gotta signify that. We're not going to put, we're not going to put a sub 1. Are we plugging in 1?
No.
Then you wouldn't put that. You plug in a 2, you gotta have a sub 2. That's where we're starting this particular sequence. When you plugged in the 2 for your n, what did you get?
1.
You got 0.
Oh, 0. Yeah.
2 minus 2 is,
0.
doesn't matter what the rest of it is, it's gonna be 0. You okay with the 0?
Yeah.
When we plug in the 3, well, if I plug in 3, a sub 3 means take your n and make it a 3. This is why our notation has to be correct, because it's telling you what you just plugged in, what you're supposed to plug in. Take that 3. What's 3 minus 2?
1.
1. Okay, now, this is negative 1 to the n, just to the third. We don't have to add or subtract anything to it. What's negative 1 to the third power, positive or negative?
Negative.
So this is going to be negative square root of 1 or negative 1. Does that make sense to you? Did you make it that far?
Yes.
Good. Let's plug in the 4. If I want to find a sub 4, I'm going to plug in 4. 4 minus 2 is 2. Now, I'm going to do the 4th power. Remember this, so for a 4, 4 goes here, 4 goes here. Negative 1 to the 4th is a positive. 4 minus 2 is square root of 2? I don't know. Just leave it.
That's what I did.
I don't know what that is. I'm not going to do 1.41 or anything. I'm going to leave it square root of 2. I want to be exact with this stuff. Quick head nod if you're all right with that one. Yes? Okay, good. 2 more. A sub 5 says, all right, take that 5, plug it in for your n. So a sub n, a sub 5, hey, 5 goes here, 5 goes here. Tell me, am I going to get a positive or negative? Negative, positive. Yeah, that should be a negative. 5 minus 2 is 3, square root of 3, I don't know. Leave it square root of 3. Next up, a sub 6. 6 is going to go here, 6 is going to go here. So negative 1 to the 6th power, positive or negative?
Positive.
For sure. 6 minus 2 is?
4.
Square root of 4?
2.
Positive 2. It doesn't end, it goes forever. Now here's what's interesting. You will find patterns in these things. First pattern we see is that the signs are changing. Positive, negative, positive, negative, positive, negative. Second one, this is just the square root of 0, the square root of 1, the square root of 2, the square root of 3, the square root of 4. Next one will be negative, square root of 5. Next one will be positive, square root of 6. Next one will be negative, and so on and so forth, and so on and so forth, forever and ever and ever and ever. Does that make sense to you? They have a pattern to it. Of course, it's a sequence. It's based on one sequence here. It's going to have some sort of a sequential order to it. Of course, we'd simplify them, which takes away that look of a pattern, doesn't it? They don't look like it has a pattern. So sometimes what that means is that if I give you this, and I want this from you. So right now I've given you the sequence, I wanted the terms. What if I gave you the terms and asked you for the sequence? Could you do it?
Yes.
Yes, but it's a little bit harder because you're not given this to just plug numbers into. Now I want you to go from here and give me this sort of thing. And that can get a little bit tricky, so I'm going to walk you through a couple examples on how to do that. But I want to make sure I've explained this well enough for you to understand what a sequence actually is. Show of hands if I have. I feel okay with that. Questions?
What's with the negative? I'm not sure what the on the top of the, like I mean negative, sorry, infinity sign.
It means it doesn't end.
Oh, okay.
So if I said, hey, you know what, I just want up into n equals 6.
So it just goes to 6.
We would have stopped right here. Not had that. Make sense?
Yeah.
Okay. Let's keep on going. So like I said, we can go backwards too. Where if I give you a list of terms, we should be able to find the sequence notation for that. By the way, it is appropriate, I didn't do this, but it is appropriate to, when you're writing out a sequence, to write these symbols as well, to show that this is the sequence that we're getting here. So we really should have that. I didn't do it, but we should have it. Say, that is my sequence. They're the same thing. You okay with that one? Okay. So, as I was saying, if I give you a sequence notation like this, where you just plug in n, this is pretty easy. It's pretty straightforward. Is it straightforward to you? Yeah. Plug in the n, it's not a big deal. But because these have a definite pattern to them, that means that from our sequences given to us term-by-term notation, we should be able to get this thing back again. And that's what I want to do with a couple examples here to give you the idea. Now, naturally, all these are going to be different. Some are going to be way harder than other ones, all right? Some of you are going to be much better at others of you, that makes sense, than others because you're good at seeing patterns. I struggled with this when I was taking this class. Man, I can't see the pattern. It took me a lot of work. It's hard sometimes to see these patterns. I'm going to give you the way that I went through this that helped me out a lot. The first thing I did was I listed out all the terms that were given to me. So I would do like, I was like a 9, it's supposed to be an 8. I would list out what a sub 1 is, a sub 2, a sub 3, a sub 4 until they stop giving me terms. Can you tell me what is my a sub 1, everybody? What's my a sub 1?
2.
Good. What's my a sub 2?
3 over square root of 2.
Very good. And then 4 over square root of 3 and 5 over square root, 5 over 2. The next thing I did was I tried to write them in all the same form. What I mean by the same form is look for a pattern that most of them have and some of them don't have and try to make them fit this format. What I mean by that is this. Most of our denominators have a square root of it around them. At least some of them do. So what I'm going to try to do here is I'm going to try to make all the denominators have a square root around them. Does that make sense?
Yeah.
That'll give us an idea of a pattern. So if I say, hey, you know what, wait a minute. Instead of 2, this is 2 over 1. Moreover, I can do 2 over square root of 1. Notice how I changed that term, the look of that term, not the value of it. It's still the same thing, right? 2 over square root of 1 is still 2, but now it more fits my pattern. Does that make sense to you? This is how I did finding a pattern. Then I would do, well, this is pretty good. This is 3 over square root 2, no problem. This is 4 over square root 3, that's not an issue. This one's a little different though. 5 over 2, I don't like that.
5 over square root of 4.
Aha, let's make that have a square root. Since that has a square root, that has a square root, probably this one's going to have a square root. But square root of 2 is not 2, square root of 4 is 2. Show of hands if you're okay with that one. So your first idea, my first idea was, let's write out all the terms. Boom, 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 boom. Let's try to make them have all the same pattern. So if I see some square roots here, I know that my sequence probably has to have a square root somewhere in there. Does that make sense? It's got to have one somewhere in there. So if I have a square root for my denominators, let's write our denominators as having a square root. 2 over 1, hey, call it square root of 1. 2, let's call it square root of 4. Now it's still square root of 1, square root of 2, square root of 3, square root of 4. Show of hands if you're okay with that one. Okay. Next idea. Try to look for a pattern that is based on some sort of an n. So the idea is, ultimately, try to relate your terms to some n. Now, when I say n, I don't mean some arbitrary number. What I mean is, look up here at the board here real quick. What's your n?
1.
Relate this to 1. Relate this pattern to 1. What's your n? Relate this pattern to 2. What's your n? Relate the pattern to 3. Does that make sense to you? So here's how what I mean by that. I mean that, well, the first part of this, for me at least, is really easy. Because what's nice is that if I see one number that always matches up, look at this, look at the board right now. 1, 1, hey, 1, 1. 2, 2, hey, 2, 2. 3, 3, that's great. 4, 4, I don't have to change that. That's brilliant. So I know the square root of 1 and square root of 2 and square root of 3 and square root of 4 means that I'm going to have a square root. So we want this, right? This is ultimately what we want to get to.
Yeah.
This is it. If I have, hey, 1, 1, 2, 2, 3, 3, 4, 4, then I'm going to have n. That's exactly right. This is the idea. We want to go from the specific to the general. We're going from the exact terms to how can I do this every time? And you can always double check your work. Okay, always double check your work. If I plug in 1, do I get that?
Yes.
If I plug in 2, do I get that?
Yep.
A sub 2, 2, 8. If I plug in 3, I get this. If I plug in 4, I get this. So what I'm doing here is I'm trying to make all these things have the same format. That way I can see a really easy pattern to it. Hopefully it relates easily to my n. Some of them don't. Some of them are hard to see. Some of them are really easy to see. This one I would say is an easy one to see. There's a 1 and a 1, a 2 and a 2, a 3 and a 3 and a 4 and a 4. You guys got it?
Yeah.
Now, we got to do the same thing with the numerators. Here I got a 2, but I start with a 1. Here I got a 3, but I start with a 2. Here I got a 4, but I start with a 3. Here I got a 5, but I start with a 4. What's the relationship?
1 plus 1.
So this is really, 2 is really 1 plus 1. Relate it to your n. 3 is really, look at this, 3 is really 2 plus 1. 4 is really 3 plus 1. 5 is really 4 plus 1. A sub n for the numerator is really n plus 1. Relate it to your n. Does that make sense to you?
Yeah.
So your idea here, and it's not as easy as probably I made it look. Okay, this one is an easy example. The idea is try to make them all the same format. If you got square roots, put square roots everywhere if you can do that. Okay? Try to relate it back to whatever your index is. So a sub 1, relate it back to 1. Relate it back to 2. Relate it back to 3, to 4. And do that with both the numerator, denominator, whatever you have. You're always trying to relate it back to the given n for that specific term. If you can do that, if you can write everything in terms of this index, everything in terms of this index, then it's really easy to write your sequence in sequence notation. You go, okay, cool. Well, look at what's happening. This is 1, 2, 2, 3, 3, 4, 4. So this is n, 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 and n. That means an n has to go here. 1, 1. The 1's not, oh, I forgot the 1. The 1's not changing. Okay, well, if the 1's not changing, we're just adding 1 to it. This is n, 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 n. That means an n has to go on the side of the square root. That means that this sequence is represented by this sequence. This is the sequence, n plus 1 over square root of n. The way that we do that, we say, hey, you know what? If we continue this pattern forever, folks, if we continue this pattern forever, every term is going to be given by this. This is the formula for every single term. That is the formula for our sequence. Show of hands if you understand that. Cool. You want to try another one?
Yeah.
Okay. Completely different topic from our integrals, isn't it? Completely different right now. We are going to see how integrals do take place in series. Not so much in sequences, it's going to be more of a limit idea. But we are going to see them eventually. But it's like a sidestep. It's a different type of thinking process. To me, it's interesting. It was hard the first time I saw it. I really didn't grasp it all that well the first time I did this. Oh my gosh, it's brand new. So if you're struggling with that, just know that you can get it. But you have to kind of switch your mindset a little bit. It's thinking outside the box some of the times. Let's do one more. Okay, so there's our sequence. The first thing that I would consider doing is writing out. I wouldn't blindly look for a pattern. Sometimes you can do that, and sometimes, oh my gosh, it's so obvious to me. That's cool. If you're that type of person, man, more power to you. That's awesome. For me, I'm not. All right, I have to go through this process. So for me, I would write out a sub 1. I would write out a sub 2, a sub 3, a sub 4. How many did I give you here? 5?
Yeah.
I'd write out all of them. And I'd go through the process. So I'd start with just the terms themselves. Well, I try to make them all the same format. Now, the same format for me means that I've got fractions everywhere. That's the idea. So I got fractions. So the only thing I do is I change this into a fraction. After that, there's no square roots. I don't see any do you see any exponents? I don't see exponents. I don't see any square roots. So as far as the format change, that's all we can do. The next thing is we got to try to relate this back to our n. We have to do that. So first thing. First thing's kind of nice. I see something as far as my pattern. Tell me one thing that you see about the pattern here.
One's on top.
Okay, there's a 1. There's a 1 always on my numerator. Well, that's going to make it kind of nice, right?
Sign change.
Oh, the sign change. That's right. So sign change. So here's the one thing I know right now. I know that my sequence is going to have terms where there's going to be a 1 on the numerator. That's what I know. You guys know that too, right? Okay, well then now that's going to change, right? It's sometimes going to be a -1, sometimes it's going to be a positive 1. So I know that here it's negative, but here it's positive. Here it's negative, but here it's positive. Here it's negative, but here it's positive. It's going to change the whole way through this. here's how we deal with that alternating idea, the alternating signs idea. Remember the first two sequences that I gave you? It was -1 to a power.
Yeah.
You're going to either do -1 to the n or -1 to the n plus 1, depending on whether you start with a positive or negative. So let's think about it. Do we start with a positive or a negative? Remember that we're always going back to whatever our n is here. Our n is 1. So what I want to know is that which one is going to give us a positive, a negative for the first term and a positive for the second term.
Top one.
Negative n to the n.
-1 to the
If I
n.
plugged in 1 here, I'd get 1 plus 1 is 2, -1 squared is positive. That would not be the correct case here. If we take away that plus 1, basically we get this one. If I plug in n equals 1, -1 to the first is still -1. That means that's going to give us this one. If I plug in a 2 here, it would give me a positive. Oh, okay. If I plug in a 3 here, it would give me a negative. Oh, okay. 4 here, positive. 5 here, negative. I'm always relating it back to my n, whatever the index is. Does that make sense to you? You sure? That's another piece of our puzzle. So we're going to do something real quick. Instead of having this 1 up here, would you be okay if I just did -1 to the n?
Yeah.
That's either going to give us a positive 1 or a negative 1. I know the numerator is going to be 1 or -1. But this gives it to us. Let's double check before we go any further, okay? Double check our numerators. Relate it back to our index. If I plug in 1, do I get -1?
Yes.
So I can move those up here even if you want. If that's helpful to you, do it. If I plug in 1, I get -1. If I plug in 2, do I get +1? If I plug in 3, do I get -1?
Yes.
4, do I get +1? 5, do I get -8? You know what? It's going to work then. We already done our numerator. Now it's just the denominator. So let's work on the denominator. Take each piece of this and relate each piece back to your n, your index. Now, right now, that looks like the n, and that looks like the n, right? Does this one look like the n? So I can't just put over n. So I put over n. The first two will be right, the rest will be wrong. I've got to have something that's right for all of them. So let's try to relate this. Sometimes it's nice to not look at the first one. It doesn't really give you a whole lot of information here. Let's look at maybe the second one on down. Do you see a pattern out of that? What do you see? Specifically, how do you get from 2 to 6? How do you get from 6 to 24? How do you get from 24 to 120? How do you get, let's try an easy one, okay? Don't add to it because there's not addition here. How do you get from 2 to 6?
3.
Multiply by,
3.
how do you get from 6 to 24? How do you get from 24 to 120?
Multiply by 5.
So what this is doing, it's taking the previous number, it's multiplying it by your n. Now, hang on a second. So this would take the previous number, the previous number doesn't exist. It just multiplies it by 1. Takes the previous number, please follow the pattern here. Takes the previous number and multiplies it by, remember you're always relating back to your n. You got it? Always. This is where it's going to get interesting. Please listen carefully. The previous number is 1 times 2, correct?
Yeah.
It multiplies it by n. The previous number is 1 times 2 times 3, correct? It multiplies it by n. The previous number is 1 times 2 times 3 times 4 times, it multiplies it by,
N factorial.
now we're getting somewhere. Can we represent this better? Yes.
N factorial.
This says take n, multiply by every number before that. That's what this is doing. It says this number is 2 times this one. This one's 3 times this one. This one's 4 times, well, all the previous ones, because that's how we're getting those ones. We're getting them by multiplying the n's from every previous term. Does that make sense to you? This is how you find the pattern, though. It's not that easy to look at it. Most people, unless you're really good at factorials, would see 1, 2, 3, 4, and 5 factorial. I did because I've done the problem before. But probably not if you're first going through it. You got to really look at that pattern. Does that make sense to you? If we do look at the pattern and go, hey, look at that. This is 5 factorial, 4 factorial. This is negative 1 over 1 factorial. This is 1 over 2 factorial. This is negative 1 over 3 factorial. This is 1 over 4 factorial. This is negative 1 over 5 factorial. By the way, if you don't know what factorial means, this is not 5! Okay? This is 5 factorial. I know it's exciting.
5 times 3 times.
Almost as good as talking about radicals. But it's not. This is 5 factorial means 5 times 4 times 3 times. It's a product of the number that I give you and every previous consecutive integer until you get down to 1. So when we relate this back to our n, we've already taken care of our numerator. It's great. It's alternating 1. Not a problem. Denominator starts with n factorial. That's what it is. Therefore, this sequence, every term of this sequence, a sub n, this is what you're looking for. You're looking for a sub n. Every term is given by this, and you should definitely double check your work before you go any further. Make sure when you plug in these numbers, you get the same thing. That'd be really silly to do this and have it wrong, okay? Plug in 1, go, yes, that gives me 1. Plug in 2, and that gives me 1/2. Plug in 3, that gives me negative 1/6. You should be doing that, okay? After you've done it, you've verified it, this is what goes inside your sequence notation. Negative 1 to the n over n factorial. And we just solved it. Have I explained well enough how to find your sequences from your terms?
Yeah.
That's way harder than finding your terms from your sequence. Okay, that's pretty easy. You just plug numbers in. It's very straightforward. The other way's kind of hard. Now, I want to give you a couple other ideas before I leave you today. The first one is a kind of an interesting idea. Sometimes we can define sequences by giving 1 or 2 or 3 or 4 or a finite number of fixed terms and then defining our sequence around those terms. For instance, if that's like, what in the world did you say in English? Here's what I said in English. Give me a couple numbers, like 2 and 4. Let's pick 2 and 4. So don't give me nothing. I'll do it on my own. Thanks a lot, guys. So I say a sub 1 is 2, a sub 2 is 4. I'm not looking for a pattern right now. I'm not thinking that a sub 3 is 8 or 6. Okay, I'm not thinking that. Here's what I'm going to define for the rest of them. I say, based on these two terms, your next term, a sub n plus 1, your next term is given by 2 times a sub n minus a sub n minus 1. And you go, what in the world is this? This is called a recursive sequence. It's called recursive because it relates back to the previous terms. A recursive idea is look back at what you had and build from there. It's based on what happened before it. So this is called a recursive sequence. The only thing I'd like to do right now is come up with the next few terms. So let's see how this actually works. It's not hard, it looks weird, okay? It really does look weird. But I want you to think about what's going on here. If you're wondering, wow, what is this a sub n plus 1? That just means your next term. So for instance, what terms do I know right now? A sub 1, a sub 2, that's what I know. So what term would I be looking for?
A sub 3.
Aha. So, watch carefully. A sub 3 would therefore be equal to, check out this, the way the recursive formula works. It says, if you want a sub 3, you're going to consider a sub 3 to be a sub, that would be 2 plus 1. So then a sub n would be just the one before it. A sub 2 minus, look at this. A sub n minus 1 would be a sub 1. Did you guys get that idea where those things came from?
Yeah.
Are you sure?
Yes.
If this is my formula, this is my recursive sequence, it says, if this is a 3, that's 1 more than 2, This is 1 more than 1. So I'm looking at these terms, a sub 1, a sub 2. Oh, that's a sub 3. Do you see how it's based on the previous terms there? It's based on what I give you. If I change these two numbers, this whole sequence changes. Show of hands feel okay with that idea. Let's find it. So a sub 3, therefore, would be 2 times, what's a sub 2?
4.
Minus, what's a sub 1?
2.
Which means that a sub 3 is...
6.
Oh, look at that. It didn't turn out to be 6. How about that? Interesting. Let's find 2 more. I'll do one more with you. I'll have you do one of your own. A sub 4. It might be helpful for you to right now write out what I did here first. This will give you a much better idea of what's going on right now. So watch this, please. I know that a sub n plus 1 says, hey, take 2 times the that's all this means. It just means the previous term. This is a sub 3, this is a sub 2. This would be a sub 1. If this is a sub 4, this is a sub 3. And this is a sub 2. It's just the previous 2 terms. So this would be 2 times a sub 3 minus a sub 2. If that makes sense to you, you got it. Do you got it? Are you sure you got it? Michael?
For that last one we did, could we have done n times a sub n minus 1, like n times the previous answer? Or would it not work in that?
This is literally what that means. Did you catch that?
Yeah, I was just wondering if we could
This
use that notation.
this is a factorial. If you didn't think about that, start with the number, take 1 away from it, take 2 away from it, take 3 away from it, multiply them all together until you get down to 1. We're actually going to use this in a minute. So, are there different ways you can define your sequence? Yeah, probably. But we're going to try to do the nicest way, if that makes sense. Did that answer your question at all?
Well, I'm talking about doing the a sub, just saying.
To define this one recursively? So like
yeah,
a sub
I
1
just
is
wondered if it
negative
made
1?
sense to do it there.
I don't know that you'd want to. I think that I'd probably want to stick with this way and not. If I don't have to define recursively, I'm probably not going to. Because I want a formula to be able to find the. Tell you what we want to do. You want to be able to find the 10th term without having to find the first 9. Okay? You can't do that with recursive sequences most of the time. Because you have to know the previous couple terms, right? To find the 10th term, you'd have to know here number 9 and number 8. Does that make sense?
Yeah.
So if you can do it without recursive, I would say do it without recursive. Now let's finish this off real quick. Do you all understand where the a sub 3 and a sub 2 came from?
Yes.
Yeah.
That's all this says is the previous 2 terms. So in our case, we'd have 2. Hey, what's a sub 3?
6.
Notice how you had to know that before you did this. A sub 2?
Minus 4. Equals 8.
So a sub 4 equals 8. How about a sub 5?
8 times
A sub 5 would be 2 times a sub 4 minus a sub 3. It's just the previous 2 terms. This is the idea of a recursive sequence. Now, please listen carefully. Is it always the previous 2? No. It can be different. It can be the previous term and then 3 before that. You just have to have it defined, okay? So a sub 5 equals 2. What's a sub 4?
8.
Minus a sub 3.
6.
A sub 5, therefore, is...
10.
So we know that this sequence goes like this. It goes 2, 4, 6, 8, 10, and it never stops. It's just the even numbers. That's exactly what that is. Show of hands feel okay with this idea? All right, good deal. So continuing on with our section, we're going to talk today about the limit of a sequence and what that infers as far as convergence and divergence. So what we need to know is that if we have a sequence a sub n, we can find the limit of the sequence. And it's going to be written as the limit of a sub n. We'll do some examples on what this means in just a little bit. As n approaches infinity. You see these sequences like this are implied to start, oh, we learned this last time, implied to start where?
1.
If I don't tell you anything, it starts at
1.
and it goes to...
Infinity.
So what we're trying to find out is what's happening to our sequence as we get bigger and bigger and bigger. Is the sequence getting bigger and bigger and bigger forever, or smaller and smaller and smaller forever, more negative, or is it tending to be towards one value? And that's what this limit idea is going to tell us. Whether our sequence is going to one number, hence it will be convergent, if the limit exists, or if it's going to infinity, or negative infinity. or whether the limit doesn't exist. In that case, it would be
Divergent.
divergent. That's exactly right. So to find out what's happening to our sequence, we take a limit. For the limit of our sequence, we're going to have a couple results. Where did I put that? If the limit exists, so equals an actual number, then we say that then the sequence is convergent. So if the limit of our sequence as n approaches infinity exists, then the sequence is convergent. If the limit does not exist, so it does not exist or is infinity. So if not, I'll say it this way. So if the limit does not exist to some number, if it's infinity or negative infinity, so if not, then the sequence is divergent. Now, a couple properties that I'm going to go through super fast. These are old properties for limits. I just want to refresh your memory on what these things. First, is this okay? Is this explained well enough for you to understand that? Trying to figure out what's happening to our sequence, right? So we're going to take a limit as the terms go towards infinity, as n approaches infinity. So way out there, we're going to see if it approaches a number or not. If it approaches a number, hey, it's convergent. If not, it's divergent. That's basically it. Now, the properties of limits. So we're going to suppose in each case that the limit of a sub n and the limit of b sub n exist. Here's what we can do with our limits. First one, if you have a limit with some constant times your sequence, what you need to know is that anytime you have a constant next to your sequence or whatever your expression is in terms of one variable, in this case it would be n, you can pull that constant in front of your limit. Next one. If you have a limit of two sequences added together, we can separate limits by addition. Number 3 says, likewise, we can also separate limits by multiplication. Well, if we can separate limits by multiplication, then we can probably separate limits by division. And we sure enough can. And lastly, number 5. Number 5 is a really cool one. I love this one. It says that if you have a limit of some sequence to a power, we'll call it p, you can actually take that power outside of your limit as well. So if you have a limit of a sub n to the p power, the whole thing's being raised to a power. This is the same thing as taking the limit of a sub n and raising the entire thing to the p power. So here's a basic rundown on our properties for limits. It says that we can pull constants out of our limits. Not a problem. We can separate limits by addition. We can separate limits by subtraction. We can separate limits by multiplication. We can separate limits by division. We can do a lot of things with limits. We can even, if we have a sequence raised to a power, we can take a limit of the sequence without the power and then take the resultant after that limit, to that power. Show of hands if you feel okay with the idea. Okay, so we're going to be using those. I know that you've seen them before. There is one qualification for this. A sub n has to be positive, and P has to be positive. So we got to check for those as well. Now, what I'd like to do is I'd like to go through some examples of how to tell when our sequences are going to be convergent or divergent. So here's what we're going to be going to. This is just what we're going to be using some of the times to deal with these limits. So the idea is going back to this. It says, if you get a sequence, let's find out what happens at the end of our sequence. There is no end, but towards infinity, what's going to happen with that? You guys ready to do a couple examples? So we're going to try to show convergence or divergence. So number one, let's say I give you a very simple sequence. A very simple sequence, like that one. -1 to the end. Can you tell me what the terms of this sequence are going to be if I were to write out the terms like we practiced last time? What's the first term going to be? -1 or -1? We'd start with 1, right? So -1 to the first power is -1. What's the next term going to be? What? How about after that? And do you see that's going to alternate forever and ever and ever and ever and ever? It's just going to be -1, 1, -1, 1, -1, 1, -1, 1, -1. Now do that for eternity, okay? What's it going to be doing after eternity?
Still 1.
Wait, is it still 1? It's going to 1? What's it doing? It's going 1, -1, 1. Is it ever getting closer to one particular number? No, it's going 1, -1, 1. And if you do this for eternity, it's still going to be doing 1, -1, 1, -1, 1, -. Is it ever going to one specific number?
No.
Then this limit can't possibly exist. This would be divergent. You go 1, -1, 1. It's never going to a specific number. Does that make sense to you? So this would say, yeah, no, there's no way. This is divergent. And that shows divergence. Good enough with that one? Now, for the other ones, this was very simple. I just want to give you the idea that not everything is convergent, and not everything, when you take a limit of it, this is one example of this, not everything, when you take a limit of it, goes to infinity, a number, or negative infinity. That's not what happens. This one doesn't go to a specific number. This is one where the limit does not exist. Does not go to infinity, does not go to negative infinity, it goes to 1 or -1, and over again. It's not going to a specific number, the limit just doesn't exist. Show of hands if you understand the concept there. Now for the rest of them, well, we have a much more concise way to do this without writing terms. We don't have to write terms with these. Here's what it says. If our sequence a sub n is given by this, 2n over n plus 1, all we've got to do is take the limit of that sequence as n approaches infinity. If the limit exists, what do we know about that sequence? Did I not explain this one? Let me explain it again. Okay. If the limit exists, we know the sequence is... Okay, so let's say we take the limit of this thing and it exists. What do we know about this sequence? Good. What if the limit does not exist or goes to infinity or negative infinity? That's the idea here. So we don't have to list out all the terms. That's not what this says. This says, hey, take your sequence. Here's your sequence. Find a limit as n approaches infinity. Let's find a limit as n approaches infinity. And if this limit exists, we know that we've just proved convergence. I need to make sure that you guys are okay with it. Do you guys see that this right here is exactly what we're doing? Just take the limit of your sequence. We're taking the limit of our sequence. This is our sequence right here. This would give us our terms, right? This would give us the first term, second term, third term, all the way to infinity. We just need to do it once and for all. We say, okay, well now let's find out what's happening to our terms. Remember that this sequence is giving us our terms, correct? Let's find out what happens to our terms as we take our n to infinity. That's the plan. Now, how are we going to do something like that? You actually could. Yeah, you could do L'Hopital. There's nothing that says you can't do L'Hopitals with this. First, you got to verify something.
It's infinity over infinity.
It is infinity over infinity. You could easily do a L'Hopitals with this. Not a problem. You could also do some old school stuff. Could you divide everything by the largest power in the denominator? You could do that. So if you divide everything by n, If you divide everything by n, we'd get 2n over n. We'd get n over n plus 1 over n. You could do it that way, or you could do it the L'Hopital way. Since we've just done L'Hopital, this way is probably going to be nice for us. What's the derivative of 2n?
2.
What's the derivative of n plus 1?
1.
What's that limit?
2.
Notice that if you were to do this, n over n is 1, n over n is 1, 2 times 1 gives you 2. What's 1 over n as n approaches infinity? So this gives you this gives you 2 times 1. This gives you 1. This whole thing is 2 as well. Remember, this thing goes to 0. Either way, you're going to get the 2. It doesn't really matter for that particular case. Show of hands, feel okay with this one. Now, here's my question. Does this show convergence or does this show divergence?
Convergence.
Why?
Because the limit exists.
Perfect. Now, does it say that this whole sequence equals 2? Sequence is a list of terms. You can't say it equals anything. It equals what it equals. It equals all the terms up to the infinity term, okay? Now, what I can tell you is that as we get close to infinity, those terms are all going to be really close to 2. That's what's going to happen. So I don't know what the actual terms are, okay? But I know that they're going to be really close to 2 as we get towards infinity. Does that make sense to you? So all we're showing here is we're not showing what this equals. We're saying the limit exists. Therefore, we have proven convergence for this particular sequence. And we just say that sequence is convergent. Okay, let's do number 3. Two plus negative 1 to the n over n. Goodness gracious. Ladies and gentlemen, how can we check for convergence or divergence of a sequence? What should we do?
Take the limit.
Limit. Don't we love the limits? No, not really. But we can do them because we've learned it from Calculus 1. So let's go ahead, let's take the limit of our sequence. What we know is that if we take the limit as n approaches infinity of whatever our sequence is, if this limit exists, we have proven convergence. If the limit does not exist, goes to infinity, or goes to something like this, we've proven that it's divergent, or we've shown divergence. Ideas?
Isn't anything with the negative 1 to the nth automatically divergent? Because
No.
No,
No,
they
it
don't
doesn't.
all equal.
Because what's
That's
happening
cute,
here is because you're taking 2 plus 1 or 2 minus 1. That's different. Okay, so this particular thing, yeah, it is doing this, but when we combine it with everything else, maybe it doesn't diverge, maybe it is convergent, we don't know. We can't just automatically jump to it, so don't jump to it, okay? Go through the process of actually finding out where the limit exists. That would be a good question, but really bad idea to do that. Now, is this infinity over infinity?
No.
No, it's not. This is 2 plus or minus 1 over infinity, okay? That's way different. So we can't use a L'Hopital rule all the time, which is why I gave you this idea. You're like, why is he bringing that up? Well, I'm bringing this idea up because sometimes we might have to actually do that in our limits. L'Hopital doesn't work all the time. It's not our fail-safe every single time. You guys with me on that one? So when you have something like, man, I have no idea. This is something over infinity. Well, to prove it, if you're really kind of thinking about this, you probably already have the answer. You probably already see what's going to go on. To really show it, though, you could divide everything by n, the largest power in the denominator. If you do that, we get a limit as n approaches infinity of 2 over n plus negative 1 to the nth over n. All over, what's this going to be? It's going to be 1. It's going to be n over n, which is 1. Now let's think about this. How much is 2 over n as n approaches infinity? How much is that?
0.
This whole thing's 0. Now, how about this one? What's negative 1 to the n over n as n approaches infinity? This is also 0. I don't care what that is, whether it's 1 or negative 1. If I divide it by infinity, it's going to be 0. Does that make sense to you? Over, can you do 0 over 1?
No.
Can you do 1 over 0?
No.
Can you do 0 over 1?
Yes.
This is 0 over 1, or 0. That's what it's saying. What it's saying is that as you're going towards infinity with your terms, all of those terms are going to get really close to what number? Yeah, I don't know what the terms are, okay, but I know that they're going to get really close to 0. Does the limit exist? Do we know what the limit equals? Well, yeah, we do. Do we know what the sequence equals? No, it's a sequence of terms. Okay, we're not adding them, we're not subtracting them. It's just it's a list of terms. But we do know that that sequence is going to converge. We have shown convergence. Show of hands if you feel okay with that one. By the way, I mentioned briefly that some of you, if you're really thinking about it, could have shown that here. That's a constant, right? That's a constant. What's a constant over infinity? Bam. Could have probably seen it right there. To show it mathematically, it should be okay, you can do this too, but you probably could have seen it. Have I explained these well enough for you? 1 through 3? You want to try a couple more? Give you some different ideas here. I kind of like these because they go way quicker right now than some of the other stuff that we've been doing that take 35 steps to do. It's kind of nice little break. How about a sub n equals ln of n over n? Oh goodness, okay. Tell me the first thing that we should do in order to test whether this thing is going to be convergent or divergent. What would we do?
Take the limit.
Very good. So let's take the limit of our sequence. Where's our limit going?
0.
I'm sorry, where's our n going?
To infinity.
Yeah, we're trying to find out what happens as we get towards infinity. Now, we don't want to find out the first finite number of terms because we could literally do that. We could plug in the 100th term and see what it is, or the 1,000,000th term, we can see what it is. What we're looking for is what's happening as we get infinitely large. We don't ever have to go to negative infinity because n is defined as being positive, right? So positive integers, don't worry about negative infinity, it's always positive infinity. That's nice for sequences. We're always growing from 1. Tell me something about the limit of ln n over n.
Can't be 0.
Almost sounds like absurd. ln n over n, whatever. ln n over n. What is it? Infinity over infinity. What we're going to use for infinity over infinity in this case? Yeah, use the L'Hopital's when you can. I didn't do it here so I could bring back another idea, but shoot, I mean, if I was actually doing this problem for real, I would definitely do L'Hopital's. Absolutely. Anytime you have the infinity over infinity, when you have those polynomials and you can actually take a derivative, or you have an ln and you can take a derivative, or some function you can take a derivative, do it. So we do a L'Hopital rule, and we get the limit as n approaches infinity of, what's the derivative of ln of n?
1 over n.
How about the derivative of, how much is 1 over n as n approaches infinity?
0.
So this thing goes to 0 over 1. How much is 0 over 1?
0.
Is this sequence convergent or divergent?
Convergent.
Because why?
Because it limits on 0
Because the limit
exists.
exists. Because it exists. That's why. So we just shown that this sequence is convergent. Still okay so far? Let's do one more and then I'll talk about something else. A couple other ideas that we can use. Good ideas. Okay, so we're trying to show whether these sequences are convergent or divergent. The first thing that we got to do is take a limit because we know if the limit exists, it's convergent. If it doesn't exist, it's divergent. So number one thing we're going to try is let's do a limit as n approaches infinity. That's what we're trying to look at. What's happening to our sequences as we get way out there of this. Now, I'm guessing that you probably haven't seen stuff like this in a while. Do you remember what to do when you have like a difference of radicals or a sum of radicals? The conjugate, that's a great word. A conjugate would be an excellent idea. If we do the conjugate here, by the way, I don't want you to just plug in infinity and go, oh, well, it's infinity minus infinity. 0! Maybe. It might be 0. I don't know. But you got to show it. Okay? You can't take a guess like that. So, anyway, a conjugate is a really good idea for this. What it does is it makes it into a fraction for you and simplifies a lot of either the numerator or denominator depending on what you're conjugating. Do you guys remember the conjugate idea for
Yes.
radicals now that we've seen it again?
Yes.
We do the same exact radicals, the sign is different, that's the That's the way that conjugates, or if you want to be fancy, conjugate. That's the way, just joking. That's the way these conjugates work. That kills my Math C class, just so you know. Actually, they go, what? Is that really what it is? Just joking. So, when we distribute this thing, notice that the reason why we use a conjugate is because we get this idea of almost get different squares out of that. The middle terms are gone, so they simplify. Also, a square root times a square root gives you the radicand. So we get n plus 1 minus n over, you just leave the entire denominator. Because what has happened here is by multiplying by the conjugate, we no longer have an infinity minus infinity. We actually change that to an infinity plus an infinity, and that we can actually do. Infinity minus infinity, I don't know. Infinity plus infinity, that's definitely infinity. Does that make sense to you? Also, what happens with our numerators?
1.
We get 1. So we've got 1 over, how much is this denominator?
Infinity.
For sure. How much is 1 over infinity?
0.
Actually, turned out that it was 0. We had to show it. By the way, if it equals 0, we got a lot of those. Do the limits always equal 0? Obviously not. But if they do equal a number, what do we know about the sequence? Good. Since the limit exists, we know convergence. I want a quick show of hands if you feel okay with these ideas. So, use what you know about the limits to find out whether the sequences are convergent or divergent. All we got to do is take the sequence, find the limit of that sequence. If it exists, cool. You know that sequence is convergent. When we get towards infinity, those terms are all around one particular number. If we do it and the limit does not exist, like that one, that means that as we go towards infinity, the terms are not all around one number. They're either growing without bound, decreasing without bound, or they're alternating, like this one is. They're not going to a specific number. In that case, we'd show divergence of our sequence, and that's basically the idea. Now, we have a couple other ways to do this. If we can't, for instance, find the limit really easily, we can use some techniques to not cheat, but be really smart about showing a comparison of a couple limits. Comparison to a couple sequences, maybe. One way that we can do this is with what's called the squeeze theorem. You ever heard of the squeeze theorem?
Yeah.
You take this limit that's bigger, and you take this limit that's smaller, you take this limit that's right in the middle, and you squeeze it and go, ha ha ha, sucker, you're going to have to go to the... If both these limits go to one thing, the limit in the middle has got to go to that one thing. We can't have these limits go somewhere, and this one go, nuh-uh. Okay, it's got to go to where these go, all right? That's what the squeeze theorem does. Now I'm going to give you what the squeeze theorem says. I'm going to show you how the squeeze theorem works in just a bit. So let's suppose that we've got 3 sequences. We have A sub n, we got B sub n, and we got C sub n. Do you notice that the B sub n is in between A sub n and C sub n for every single term? This is what this means. So this means that for all these terms and all these terms sequentially, this one's always going to be between them, every single time. So for the first term, it's this scenario. For the second term, it's this scenario. And every single time, every single term until we get to infinity, it's always going to be A sub n smaller than B sub n, B sub n smaller than C sub n. Does that make sense? Furthermore, let's assume that the limit of A sub n equals the limit of C sub n, and that those limits both exist. That's why I'm putting an L there, that it's actual existence of those limits. They exist. Does that make sense to you so far? Did I just lose you? I don't want to lose you here. It says that, hey, suppose that this is the scenario. We got the sequence we're going to be trying to show right now is the B sub n. We're going to assume that we know what this limit is, that it exists. We're going to assume that we know what the limit of this sequence is, and that it exists, and that these two limits are the same. So basically, these two are going to the same number. Does that make sense? They're both going to L. Well, if that's the case, if the limit of A sub n goes to L, and the limit of C sub n goes to L as n approaches infinity, tell me something about the limit of B sub n as n approaches infinity.
Goes to L.
It has to go to L. It's squeezed between them. So again, this says, these two guys, these are doing this. A sub n's going to one number, B sub n's going to the same, C sub n, I misspoke. A sub n's going to one number, C sub n's going to the same number. B sub n is somewhere between those guys, right? Somewhere between there. So if these are going like this to one number at infinity, this one's also got to go there. Does that make sense to you? That's the way squeeze theorem basically works. So, let me show you an example about how we can actually use it. It's going to take us some time. Do you have any questions on this so far? I'm going to leave this one and start over here. Questions on these ones? Are they straightforward to you? Good, okay. I actually asked you for questions before I erased it this time. I'm learning. You know what, I'm going to call it, I'll call it A sub n. Let's do that. We got A sub n equals n over n to the n. I'm so excited! Factorials! Super! No, it's not n. It's n factorial. Now, here's the thing. If we were to go through the same process that we just did, the idea of finding out whether this sequence is convergent or divergent would be, well, you take a limit, wouldn't you? Wouldn't you?
Yes.
So we'd say, hey, what's the limit as n approaches infinity of n factorial over n to the n? And you think about it, and go, okay, as we go to infinity, we're going to have, hey, what's n factorial as n approaches infinity?
Can you just solve for it?
What's n to the n as n approaches infinity?
Infinity?
Solve for n.
Wait, no.
It's definitely infinity to the infinity is going to be infinity, all right?
Okay.
So we have an infinity over infinity.
Tricked me with this bit.
However, if we divide by the largest power in the denominator, we're dividing by n to the n, right? We'd get exactly the same thing over again. We get n plus n factorial over n to the n, over 1. That wouldn't help us. If we try and do L'Hopital's rule, this thing explodes, this thing we don't know how to do derivatives of n factorial. So maybe we have a better way. If we have those factorials, we go, oh my gosh, I have no idea. Maybe we try to do a squeeze theorem on it. Try to find something that is smaller than this and something that is bigger than this. So here's what I know. I'm going to start off on one, you know what I'm going to do? I'm going to start off right here on one side. I'm going to use the rest of the board to kind of work down to here. The one thing I know is that this is always going to be positive. Would you agree with that? Always positive. So I know right off the bat that 0 is less than or equal to my sequence. That's what I know. Now, the goal then is to find some other sequence that goes right here that the limit of it is what?
1?
Not 1.
Oh,
I'm trying to squeeze it, right? If I'm going to squeeze something, these two limits, the limits of these sequences have to be the same. So since I've bounded this below by 0,
oh, 0.
it's got to be 0. If the squeeze theorem is going to work, it would have to be. Do you understand the squeeze theorem?
Yes.
If I say, hey, tell you what, one sequence goes to 0 and one goes to 100, what's this one go to? I don't know. How am I supposed to know that? I don't have no idea. Doesn't make any sense. If I say this one goes to 1 and this one goes to 1 and this one goes to 1, that's how squeeze theorem works. So we're trying to go to the same number. So if I say, I know that this is positive, therefore it's always greater than or equal to 0, not a big deal. I also need to find a sequence over here that the limit of that sequence goes to 0 as well. That's when the squeeze theorem is going to work for us. You guys with me on this? Now, in order to get started, maybe we start by looking at the first few terms of what the sequence actually is doing. We didn't have to do that with our previous examples, but here it might be a good idea. Also, I'll tell you this, when I'm looking at terms of my sequence, I'm not simplifying them. I do not simplify them and make it like one number over another number. I leave them in their form that, I'll show you right now. I'll leave them in a form that way I can see the pattern and maybe come up with some comparison. So, for instance, a sub 1 gives me 1 over 1 to the 1.
One.
Does that make sense?
Yes.
I know that equals 1, but I'm going to leave it right here. This a sub 2 gives me 2 times 1 over 2 times 2.
To the 2 power.
That's right, 2 to the second power, or 2 times 2.
Oh.
Does that make sense to you? A sub 3 gives me 3 times 2 times 1. Do you guys know what factorial means? 3 times 2 times 1? Over 3 to the third, right? But that would be 3 times 3 times 3. Does that make sense to you? Yes, no. Yes, no.
Yes.
Okay, so here's the thought. I'm going to do something kind of tricky. If I think about this, I know that this one is always going to be less than or equal to 2 times 2 over 2 times 2, isn't it? And this one's always going to be less than or equal to 3 times 3 times 3 over 3 times 3 times 3, isn't it? You sure? Now, one more thing. This is going to be kind of interesting here. Because the last number of a factorial is always 1, always, do you understand that? Last number in a factorial is always 1. I can actually eliminate this last term, and it's still right. Does that make sense to you? You can even try it with a sub 4. A sub 4 would be, let's see, 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. I know that's less than or equal to 4 times 4 times 4, but look at, the last number's 1. I don't even need that. Over 4 times 4 times 4 times 4. Here's what I'm trying to get you to see. If I do a sub n would be n factorial over n to the n. Well, what I know is that this is equal to, less than or equal to, the denominator I'm not going to change, but here's what I know about the numerator. The numerator is always going to be less than n to the, not n to the n to the n minus 1. I know that for sure. I got a different way for you guys to see that too if you want. If you wanted to look at it differently, so did that blow your mind, or were you able to follow that? Did you get that? How many people got that? Feel okay about that? Did I blow anybody's mind? You're like, oh my gosh, what in the world just happened? Okay, check it out. Let's think about what n factorial means. Let's think about what n to the n means. Would you agree that this is always less than or equal to this one? Always. Because this is n times n minus 1 times n minus 2 times forever. Does that make sense? But this one is n times n times n forever. Does that make sense to you? Are you sure? Now listen carefully if you didn't get this the first time. Here's the whole idea, okay? Here's the whole idea. How many terms are here? All the way to, how many terms are going to be there?
Infinity.
Not infinity. I'm going to go to n. So if I give, for instance, if I gave you 3, how many terms are here?
3.
If I give you 4, how many terms are here?
4.
There's going to be n terms here. They're n terms. N terms. Did you guys get me on that one? Are you sure? How many n's are going to be over here?
Same.
N. There's going to be n terms. Now, here's the part where we think a little bit. Do you agree that the last term over here is going to be 1?
Mm-hmm.
Okay, so there's n terms, but the last one is 1. 1 is going to be less than or equal to any number in the world. Any number. A whole number, a whole integer number positive in the world. Yeah, let's qualify that a little bit. Basically, it's going to be less than any one of these, correct? So because our last term over here is n and our last term over here is 1, I can take away this last n. I can take away that last n and I'm still bigger than this because my last term here is 1. Does that make sense to you? So then I'm going to say, tell you what, this had n terms, but this would still be true if I had less than, so here's n terms here. Last term is 1. And then I did this, where I only have n minus 1 terms. So I say, let's compare these. I know this is true. I know this is always going to be greater than or equal to this one. Obviously, this is counting down. This is 5, 4, 3, 2, 1. This is 5, 5, 5, 5, 5. This one's always going to be bigger than that. Understood? However, I can be a little bit better. I can say, well, I know that if this is 5, 4, 3, 2, 1, that last one, who cares? I can do 5, 5, 5, 5, and it's always still bigger than that. Because the last term here is 1. Does that make sense to you? So I go, all right, well, I think about this as n factorial, but I think about this as not n to the n. How about n to the n minus 1? So what this gives us is that n factorial is less than or equal to n to the, please listen carefully so you understand where I'm getting this from. If this has n terms, this is n to the nth. Does that make sense to you? If this has n minus 1 terms, this is n to the n minus 1. Show of hands if you feel okay with that. Is that a little bit, did I explain a little bit better for you the second time around? Questions, if you have them? Are you sure? Because I want you to get it before I go any further. It's kind of an important idea. I'm going to keep this on the board, just work right down here. All right, well then if this is true, what we know about inequalities is if I divide both sides by the same thing, as long as it's not negative, I still have a valid inequality. Since n to the n is always positive, I'm divided by a positive, my inequality is still good. We okay with this one? Now, here's the cool part about this. Can you find the limit as n approaches infinity of n to the n minus 1 over n to the n? Yeah, we can do that actually. What we would do is we would now divide by the largest power in the denominator. If we divide by n to the n on both the numerator and denominator, we get a limit as n approaches infinity of, well, this would be n to the n minus 1 over n to the n, all over n to the n over n to the, oh my gosh, there's a lot of n's. That was really stupid. Why did I do that? That was really dumb. I'm sorry. I was just going through my process. That was ridiculous. We can do it a lot easier than that. Actually, don't write that down. Edit. What did I want to do? Oh yeah. If you think about what this is, think about what n to the n is. If I split off one n, just one n, then this is n to the n minus 1 times n. Do you buy into that one? What do you do when you multiply common bases? You add the exponents. What's n minus 1 plus 1? Hey, this is true then. What's n to the n minus 1 over n to the n minus 1? This is gone. You get 1. How much is the limit of 1 over n as n approaches infinity?
0.
That's 0. So let's put all of this stuff together. What we know from here is that 0 was less than a to the n, a sub n. We now know that a sub n is less than, well, it was less than this sequence. N to the n minus 1 over n to the n. Because the limit of this, what's the limit of 0? 0. What's the limit of this one?
0.
Because this goes to 0, and because this goes to 0, this says that the limit of a sub n as n approaches infinity goes to 0. What's that tell you about our sequence? Is it convergent or is it divergent? It's convergent. I can tell by some of the looks on your faces Some of them are like, and some are like, because you just kind of gave up on the problem. I want to make sure that you get it, all right? I don't want to just leave you hanging on this stuff. That's right. I won't leave you hanging on this deep stuff. Did you get the idea at all?
Yeah.
Whatsoever? Or are we just...
It's just processing stuff.
There's a lot, right? There's a lot of stuff that we just did. We learned about the squeeze theorem. Squeeze theorem says these go here, this goes here. So we make it up. We go, okay, cool. I know that my sequence is going to be greater than 0. I know that because I just looked at my terms, look at this, look at my terms. This is n factorial, right? Look at the terms, please. This is n to the n minus 1. I'm stopping before the last one. This is still true. This is still less than this. Well, that shows you that n factorial over n to the n is less than n to the n minus 1. I'm stopping before the last term. N minus 1. Hey, look at that. We got the same thing over there. N minus 1. I'm stopping before the last term because the last term here is 1. It's not going to make a difference what I have. This is always still, it's still going to be a valid inequality. The limit of this guy is 0. Got it? Just showed it right there. Just showed it right here. Just split off the n to the n minus 1 times n. This is still n to the n. These are gone. We get 1 over n. Limit of that's 0. So I've shown that 0 goes to 0. I've now shown that a sub n is less than or equal to this. A sub n is less than or equal to this. But this guy goes to 0. Therefore, if 0, the limit of 0 is 0. The limit of this is 0. Therefore, we now have a sub n bounded between two sequences, two different sequences, but both of them go to the same thing. 0 goes to 0. This limit, or the limit of this sequence goes to 0. Therefore, the limit of our sequence itself goes to 0, and that proves that that thing is convergent, and that's the idea. Should fans feel at least a little bit okay about that one? Okay. Any questions at all before I move on? You see, what I want to give you right now is two pieces of information that are very useful for you that we can use all the time from here on out. Here they are. Any less chance. This is all going bye-bye. Did you get this? Got that idea? It's kind of cool, right? Split that off. Okay, so 2 notes with a couple examples, very, very fast examples here. This one is very cool. We're actually going to use this later on as well in series. But here's what you need to know. If the limit of the absolute value of the sequence equals 0, then the limit of the sequence itself also equals 0. You're like, so what? Firstly, why in the world? What are you kidding me? Here's what this is. I'll give you kind of a rundown, okay? Look, if you have a limit where you take the absolute value and it equals 0, if you have something that looks like this, where it's going positive, negative, positive, negative, positive, negative, positive, negative. If you change all these to absolute value, you get something that looks like this. Does that make sense? Down to 0. So this says if the limit of the absolute value of the sequence goes to 0, then even though this sequence originally looked like this, that's still going to 0. That's what that says. So the way we use it is with something like this one. You go, okay, cool. Let's talk about the limit as n approaches infinity. So suppose we got this sequence, -1 to the n over n. Suppose we're given that, and we go, okay, show convergence or divergence. And you go, I don't even know, because it's alternating, right? I don't know. Well, I mean, you could just divide everything, but, or you could think about it. This is alternating between 1 and -1. That's a constant number. This is infinity. It's going to be 0 for sure. But we can actually prove it with this, and this is very useful a lot of the times. Well, just consider this one. Consider the limit as n approaches infinity of -1 to the n over n in absolute value. Consider that one. Tell me what happens, ladies and gentlemen, with negative 1 to the n if I put it inside absolute value. What's it going to be? It's not going to be 0. It's going to be 1. It says, hey, take positive 1, take the absolute value. It's 1. Take negative 1, take the absolute value. It's 1. And I don't care what we do with n, because absolute value of a positive number is always positive. So it's really not for the n. N is always positive. Does that make sense to you? Always positive. Therefore, this would be equivalent to the limit as n approaches infinity of 1 over n. Tell me, what's the limit as n approaches infinity of 1 over n?
0.
Absolutely. And here's where our little theorem comes in. It says, check it out. It says take your sequence, whatever you had, take the absolute value of your sequence. Okay, here's our sequence. Let's take the absolute value of our sequence. If this limit works out to be 0, what's it tell you about this limit? It's also 0. So, the limit as n approaches infinity, negative 1 to the n over n, is also 0. If the limit of the absolute value of our sequence equals 0, the absolute value of the sequence equals 0, the limit of the sequence itself also equals 0. Show of hands if you feel okay with that one. That's real nice to get rid of the negative 1 to the n real fast. You can do that a lot, okay? And we will be doing that a lot. Okay, last one. We've actually already used this. Very cool little theorem here. It says if you have a continuous function and you have a limit of a sequence exists as n approaches infinity, then if you have a composition, so basically you have this, okay, you have a sequence, look at the board here real quick please so I can explain this. You have a sequence whose limit exists inside of a continuous function. We've actually used this before. You will notice on the next example that we do, we've seen this before. We had e to the ln. We had limit of e to some function. We pulled the e outside the function. Remember doing that? I said, oh, you can do that because it's continuous. I never really proved it. I never really showed it. Here's the reason why. If you have a function that is continuous, and you have a limit of a sequence that actually exists, and you have a limit of, well, let's suppose that sequence is inside a continuous function, you can actually pull that function out. Do the limit first. Which also means that if this limit exists, which is kind of cool, all you have to do, all you got to do is find the limit, plug it into the function. Done. Let me give you a couple examples of this real fast because I do not want to leave you hanging on this stuff, and then we'll be done for today. True or false? The function e is a continuous function. True or false?
True.
E is always continuous, from negative infinity to infinity. It just does, it's always continuous. Because it's continuous, so e to the x is continuous. Let's talk about the limit of sine of 1 over n as n approaches infinity. Please be careful and don't rush off to something silly with sine. I know that sine does this. I know it does that, okay? But look at what's going in. Look at the argument of sine. All right. Check this out. As n approaches infinity, what's 1 over n approach? 0. What's sine of 0? Did you guys get the idea here? N is infinity. Therefore, 1 over n as n approaches infinity is 0. This is approaching 0. What's sine as sine approaches 0? 0. 0. Hey, does the limit exist? exists. In fact, it's convergent. Here's the cool part. Here's where the theorem comes in, okay? Check it out. It says if the function is continuous and the limit exists. The function is continuous and the limit exists. Agreed?
Yeah.
That means that from here, we could actually do e to the limit of sine 1 over n as n approaches infinity. Or basically, think about this. Look at the board here real quick. This limit is 0, right? Therefore, we would just have to plug this into the function. E to the 0. How much is e to the 0? 1. Isn't that rad? Kind of cool. Okay, last one and then I'll let you go. Promise. Oh, you're right.
Do it.
Good doing you.
You can leave.
If you must go, go. I got to do this one because we're right here. So if you got to go, go. You're not going to offend me. But this is going to take us about maybe 2 minutes. So first thing, is tan inverse of x continuous? Yes, no?
Yes.
Yes, it is. Tan inverse looks like this. It is continuous. Can you find the limit of n squared as n approaches infinity? Okay, this part is, yes. But what is it?
Infinity.
It's not a trick question. What is it?
Infinity.
Okay. So it exists. It's not convergent, but it does exist. So this is continuous. This exists. Here's what this says. If I want to find the limit of tan inverse of n squared as n approaches infinity, then all I got to do is find tan inverse of the limit as n approaches infinity of n squared. Now check it out. Okay, watch careful. This is the only thing we gotta do, okay? Tan inverse is continuous, agreed?
Yeah.
That means that if I take a limit of it, I can pull that limit out in front, pull that tangent inverse outside of my limit. So it says this is continuous, this exists, yes, it's infinity. So let's pull that tan inverse out front. What's the limit of n squared as n approaches infinity again? So what's tan inverse? It's not good math to write this, but what's tan inverse of infinity? What happens as we go towards infinity? What's this going to? Pi over 2. That's right, pi over 2. Is that interesting or what?
Wow.
Did that make sense to you? So fans feel okay with what we talked about today? Good deal. All right. So the last little bit of our section here on sequences. Talks about one specific type of sequence. It's called a monotonic sequence. And what monotonic means is a sequence, as far as a sequence goes, is a sequence that is always increasing or always decreasing. So monotonic means you start with one term of your sequence and it either goes higher and higher and higher and higher every single time, or it goes lower and lower and lower and lower every single time. It either grows forever or it declines forever. Does that make sense to you?
Mm-hmm.
That's what monotonic means. That's the definition of it. So a monotonic sequence is a sequence that is always increasing or decreasing. A sequence that is always either increasing or is always decreasing. What we mean as far as always increasing or always decreasing in terms of our sequence, it would mean this. If a sequence is increasing, then if I have a sub 1 and I have a sub 2 and I have a sub 3 and I have so on and so forth, well, if it's always increasing, then a sub 1 has to be less than a sub 2. And a sub 2 has to be less than a sub 3. And a sub 3 has to be less than forever and ever and ever. A sub 4 forever and ever and ever. That would be the idea of increasing. It'd start off and then the terms get bigger and bigger and bigger and bigger forever and ever and ever. Does that make sense to you? Okay. Decreasing, of course, would be the other way. To say, well, you're starting off with some terms here, but if you're decreasing, then the first term would be bigger than the second term, which would be bigger than the third term, bigger than the fourth term, forever and ever. And that's a definition of a monotonic sequence. It's a sequence that where the terms either grow or decrease, increase or decrease forever and ever and ever. Should fans feel okay with the idea of a monotonic sequence? Very good. Now, what's going to be important for us is the act of showing whether a sequence is either always increasing or always decreasing. We got to prove it, because what we're going to be doing in just a minute, here's like the advanced organizer what we're doing. We're going to talk about monotonic sequences. We're going to talk about whether or not they are bounded or, whether they're bounded or not. If we have a monotonic sequence that is bounded, we can say certain things about that. But in order to say that it's monotonic, we've got to show that that sequence is always increasing or is always decreasing. Does that make sense? We got to prove this or we got to prove this. I'm going to give you a couple examples on how to do that. Then we'll talk about convergence as it relates to monotonic sequences. I just said a whole bunch of words. Were you following all that stuff? So number one thing we got to do for monotonic sequences is show that they are increasing or decreasing. For instance, and I'm going to give you two methods on how to do this. Two pretty good methods. So right now I want to show that this sequence is increasing. If you were to get this on your own, and you go, well, wait a minute, I don't know whether n over n plus 1 is always increasing, always decreasing. You might have to plug in a couple terms and figure out what's going on. So I'd plug in, like, I don't know, 1. And I'd plug in 2, 3, 4, 5. I'd see what's going on here. Is this increasing? Is this decreasing? It turns out that these fractions are getting bigger and bigger and bigger. They're increasing here. Does that make sense to you? Okay, so if we want to show this is always increasing, there's basically two ways to do this. One way to do this would be to consider, start with the nth term. And if we want to show that this is increasing, listen carefully to this because this can throw some people if you're really not with it right now, okay? If you're trying to show increasing, your first term or your nth term should be less than, you could be less than or equal to your next term. Now here's the question. How would I get my next term?
N plus 1.
N plus 1. So for instance, if this was my third term, I'd have 3 and 3, correct?
Yeah.
That would be less than my fourth term, which would be 4 and 4. That would be 3 plus 1. If I had my 11th term, it would be 11 and 11. That would be less than my 12th term, which would be 11 plus 1, 11 plus. So basically, anytime you're trying to do this, compare it to your next term. Your next term is just, well, whatever you had, because we're dealing with whole number integers, add 1. That would be your next term. Over, what would this be?
N plus 1.
2.
Okay, n plus 1 plus 1. I heard that. N plus 1 plus 1. Now, of course, we're going to make that a little bit simpler, aren't we? Sure, n plus 2. A show of hands if you feel okay with that as our next term. So let's think about it. Here's our nth term. We got to be general, right? We can't plug in just 1 and plug in 2 because that would show that it's increasing only for one set of terms between a sub 1 and a sub 2. That doesn't make sense. We got to show that this is increasing for all of our terms. So for our nth term, is it still increasing from n to n plus 1? So we say, okay, here's our nth term. It's just our sequence. The next term would be add 1 to the n. Well, that's going to be the next number past whatever you say. If you give me 4, I give you 5. If you give me 11, I give you 12. I'm just adding 1 to whatever you're doing. And that gives us our next term. n, okay, to n plus 1. n plus 1 to n plus 1 plus 1, or n plus 2. And if we're trying to show that it's increasing, this term should be bigger or smaller than this term?
Bigger.
Should be bigger than this term. Now, if we simplify it just a little bit, we've got this. So basically, we're trying to prove that this is true. Now, here's some things that we can do with it. If we're simply trying to prove that this is true, we can manipulate these two sides to make it mean something a little different, or make it mean, make it look a little bit nicer for us, I should say. Something that's easy to identify what's happening. Because right now, like, well, I don't know. Is it obvious that this is bigger than this? Not really, not super obvious, because I'm adding one of this, but I'm adding one of that. I don't know. So maybe we do things like, let's multiply both sides by n plus 2. Let's multiply both sides by n plus 1. Essentially, we're going to take this and put it here, and take this and put it there. Is that legal to do? Okay, you have to be careful. It's legal to do with inequalities here only because this is what type of a number? Positive or negative? If you multiply both sides by a negative, do you remember that you flip your inequalities? Okay, now think about what n is. When we defined n is positive, correct? N plus 1 would be positive, n plus 2 would be positive. So by multiplying by n plus 2, we don't have to worry about an inequality because we're multiplying by a positive number. Does that make sense to you? Multiplying by n plus 1, we don't have to worry about an inequality because we're multiplying by a positive number. So if I multiply both sides by n plus 2 and n plus 1 respectively, I get n times n plus 2 is less than or equal to n plus 1 times n plus 1. If I had multiplied by negatives, I'd have to flip my inequality. Because I'm multiplying by positives, I don't have to do that. Show of hands if you're okay with this so far. Now, this is a little bit better, but let's go ahead and distribute and really see what's going on. If we distribute, we get n squared plus 2n. We get less than n squared plus 2n plus 1.
It's bigger.
Do you know that this is bigger than this side?
Yes.
Is it true for all n bigger than 1?
Yes.
So since this is kind of cool. This is true for all n greater than or equal to 1. The reason why this comes about is because, hey, where do our sequences typically start? And they go forever, right? So we don't really care about 0. We don't really care about negatives. I don't care about that stuff. I care about positive numbers starting at 1 because that's where our sequences start. So if I can show this for, are you listening right now? If I can show this for 1 and more, then we're good to go. Make sense? So if this is true, well, this came from this guy, this came from this guy. So because we manipulated this, we didn't change around our inequality, we did all valid work with our inequalities here. It says because this side is bigger than this side, it says this side is bigger than this side, and that right there shows that we are increasing. For every n that's greater than or equal to 1, and that's all that counts because with our sequences we start with n greater than or equal to 1, and they're always positive. Show of hands, feel okay with this so far. So what we've just shown here, we've shown that this is increasing. This proves that this sequence is always increasing. We were general, we had n's, we didn't use specific numbers, we're good to go. You sure you're okay with that? Okay. Would you like a different way to do it?
Yes.
So it's true for all this, that means that this is increasing. Sometimes, not all the time, but sometimes we can use a very interesting idea to show increasing or decreasing. Here's another way to think about it. So, or. I'll make a little caveat box. Or. What if we had a different thought? What if we said, you know what, I don't want to think of this like a sequence. In fact, if I just think of this not as a sequence, but pretend that it is a function of x. So basically, instead of having n over n plus 1, I think about a function of x, x over x plus 1. Where I've got a function in terms of x. Got a function in terms of x. Here's the interesting thought. But firstly, does this look something like that to you? Now you need to understand something. This is not this. This is a function. In fact, it's a continuous function everywhere besides x equals negative 1. Understood? It's continuous for 1 and more, actually, which is kind of cool. This is not a continuous function. These are just fractions. This is a list of fractions. That's all that this is. So what we're doing here is we're kind of making this thing into a function to find out whether it's increasing or decreasing using this one idea. Back in your Calculus 1 class, could you tell me when a function was increasing and when a function was decreasing?
Yes.
And what did you use to do that? Derivatives. And you use specifically the slope, which is what? What is the slope of a function in terms of calculus?
Instantaneous rate of change.
Okay, you're right. It's an instantaneous rate of change. How do we find the slope or instantaneous rate of change? It's the first derivative. In fact, when you did, it was one specific chapter for us, it was chapter 3. It's called the first derivative test. Remember the first derivative test? Where you take the first derivative, and and for us, we would set it equal to 0. And that would say where you're changing from increasing to decreasing. And you plugged in two numbers. If it was positive, if your first derivative was positive, that meant your function was increasing. Do you remember doing that?
Yeah.
If your first derivative was negative, it meant your function was decreasing for that specific interval. And that was nice. We're going to use the same idea here. If the first derivative gives us the rate of change, if the first derivative gives us increasing or decreasing, then we can use the first derivative here. Here's how we do it. If we did the first derivative, now, you got to know how to take the first derivative. This is not a L'Hopital thing, okay? This is a derivative now. We haven't done this in a long time. How would you do the derivative of x over x plus 1? Low d high minus high d low, square the bottom, and away we're done. I kind of messed that up, didn't I? And away we go. So low d high minus high d low, square the bottom, away we go. Now, of course, I'm going to do this kind of quick, right? Because we're supposed to be really good at derivatives at this point. The first derivative, therefore, would be 1 over x plus 1 squared. Show of hands if you feel okay with that one. Now, you need to understand something about this. A first derivative is a slope. It is a rate of change. It's a formula for the slope, or the formula for the rate of change. So basically, if the first derivative is positive, it means that our function is increasing. If our first derivative is negative, it means our function is decreasing. Are you all with me on this?
Yeah.
Here's my question. Look at this. Is this positive or negative or both? Oh, you should know. Plug in any number in the freaking world and tell me if it's positive or negative. Is it always positive? Forever. For anything. Now, we don't care about forever anything. Be real careful here. We care that this is greater than 0 or less than 0 for x. What x's do we care about? Do we care about negative x's right now?
No.
Do we care about when x is 0? We care about when x is greater than or equal to what?
1.
To 1. Now, here's why this works for us, just so you know. We're taking this thing, this sequence, and calling it a function. We're saying, let's find the first derivative of the function. If the first derivative of the function is positive, it means the function is increasing. If the first derivative of the function is negative, it means the function is decreasing. Now, we're saying x equals 1 because really our sequences are going to start at 1. Now, we're going above and beyond here when you think about it. This thing is not a sequence, correct? So I can plug in 1 and 1.1 and 1.0003 and 1.5 and all these numbers in between 1 and 2. So we're basically going above and beyond what a sequence does. Let me make the point here for you. If this works for all x's, for x greater than or equal to 1, it's certainly going to work for x equals 1 and 2 and 3 and 4 and 5 and 6 and 7 for when our n equals our x. Does that make sense? Or when our x equals our n. For all the whole number integers. Show of hands if you see the comparison here. Okay, good. So we're using the function to say, hey, if it works for everything, it's certainly going to be increasing for all the positive integers, and that's what our sequence does as well. So we use the function to kind of cheat at the sequence and say, hey, if that's increasing, that's certainly got to be. You just can't call it an n because we're talking about a function here, not a sequence. So far, so good? Okay, so last time. So for x greater than or equal to 1, this is always true. It's actually true anywhere, but I don't have to have it anywhere. I just have to have it for x greater than or equal to 1 because that's where our sequence starts. So since this is greater than 0, this shows increasing as well. So there's really two ways to do it. You can consider a term and the next term and see what's going on. You can consider a derivative of some function that's based on your sequence and look at what's happening. Have I explained this well enough for you to understand it?
Yes.
Oh, okay. Would you like to try another example?
Yes, please.
So now, on this example, I asked you to show that that's increasing. I kind of gave you a heads up and said, tell you what, this thing is going to be increasing, you just need to show it. Well, that kind of gave us a clue as to what to do here, didn't it? It said, certainly you're going to have to determine the next term. You have to have it anyway. But we were looking for this. We manipulated it to see that relationship. This one, well, we could have done that either way, couldn't we? If we just found the first derivative, it would have shown up that that's positive. It would have shown up that, hey, if your first derivative is positive, your function is increasing. If your function is increasing, the sequence upon which that function is based must also be increasing for that interval. Well, that means that if I give you a function, or a sequence, I'm sorry, if I give you a sequence and say, just tell me whether this is increasing or not, whether it's increasing or decreasing, we might not want to start with this. We might want to start with the derivative, because that'll give us the answer typically every time. Now, we can't always do a derivative. I'll show you some examples where we can, okay? But if you can, it might be a nice way to start this. So why don't you try, firstly, to call this a function in terms of x. Again, we're using a function in terms of x and not in terms of n, because n stands for our sequence. It's the terms where n is based on 1 and 2 and 3 and 4. We're saying a function of x, saying, now this is going to be hopefully a continuous function for 1 and more. We're looking for a continuous function here. If that's the case, if our function is continuous and our function is always increasing or decreasing, then our sequence is so as well. But we can't call it in terms of n. It's not the same thing. So we are making a function in terms of x, just basing it on the sequence. What would a function in terms of x look like? Can you tell me?
X over E of X.
Okay, very good. Now, what's the next idea? What are you going to do? Say it louder so I can hear you. Why are you going to take the derivative?
To see if it's increasing or decreasing.
Yeah, a derivative gives you slope. Positive slope means increasing. Negative slope means decreasing. Go ahead and do the derivative. So quotient rule, oh my goodness, we haven't done quotient rule in a while. Low d high minus high d low, square the bottom, away we go. Don't just take a derivative of the numerator and derivative of the denominator. That's L'Hopital's rule, and that's not what we're doing here. Mr. Rob, is that what you did? Low d high minus high d low, square the bottom, and away we're done. Got it. Away we go. Did you get that?
Yes.
Well, that's really hard to see what's going on, so maybe we start factoring and simplifying a little bit. If we simplify this, we can factor out the e to the x. Can you simplify the e to the x's?
Yep. Yes.
This is gone, the 2 is gone. Remember that e to the x squared is e to the 2x. That's where that's coming from. So this is the same thing as 1 minus x over e to the x. Now, we need to think about what is happening for the required domain of our function. The domain of our function is x is what? Greater than or equal to 1. Yes, no?
Yes.
Greater than or equal to 1. Why is it greater? Why? Why do I have it defined as x is greater than or equal to 1?
Because n's are positive.
Because our n's start where?
1.
And they go higher. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's why this is defined that way. I'm trying to define my function as starting with my sequence. Because if this is increasing or decreasing for this entire domain, then the sequence is increasing or decreasing for every single n, because all n's would fit somewhere in this domain. Make sense? So let's think about it. What's e to the x? Is that positive, negative, or what? If I now keep in mind, if I'm plugging in 1, 2, 3, 4, 5, 6, 7, is that positive or negative?
Positive.
That's always positive. So no matter what I plug in, that's positive, correct? Now think about this one. 1 minus x, where x is 1 and more. It's 0 for 1. But then after that, what is it? And after that, what is it? After that, what is it? Is it always negative?
Yes.
So this is always less than or potentially equal to 0. For x is greater than or equal to 1. Oh, goodness, that's so cool. What's it tell you about this function? Is it increasing or decreasing?
Decreasing.
For all x greater than 1, yes?
Yes.
Actually, it makes sense.
Hopefully it makes sense. I'm teaching it. Shoot, come on now. So if this is always negative for x greater than or equal to 1, then that function is always decreasing for x greater than or equal to 1. So that sequence is always decreasing for n is greater than or equal to 1. You see the jump? We just shown that function is decreasing all the time. Now here's the whole, what we're trying to get to. Have I made this make sense to you? Any questions about this side? Here's what we're trying to get to. Being monotonic is awesome, I guess. I'm always on the upshot, so I'm monotonically increasing, whatever. Sucks to be monotonically decreasing, what a loser. But anyway, what we're trying to get is we're going to put two ideas together. This idea of being monotonic and this next idea of being bounded. A bounded sequence. For some sequence, if a sub n is always less than some number, if a sub n is always greater than some number, if a sub n is always between two numbers. What bounded means? Bounded means this idea that the sequence is contained somewhere. The sequence never goes above a certain number. The sequence never goes below a certain number, or the sequence is between two numbers forever. Does that make sense to you? That's what bounded means. So here's what we say. Tell you what, if every term of our sequence is less than 7, or 10, or -4, or whatever it happens to be, if every term in our sequence is less than a certain number, one finite fixed number, we say that sequence is bounded above. Why? Because it's got a ceiling. You guys get what I'm saying here?
Yeah.
It's got a ceiling there. The ceiling is m. This would be bounded above. Now let's say that our sequence, I'm using uppercase m and lowercase m, just so you know. I write in all caps, so it's really hard for me, but that's supposed to be lowercase m. So, if every term of our sequence is always bigger than a certain number, every term is always bigger than 1, or bigger than -3, or bigger than 0, maybe, it's got a floor. It never drops below a certain amount. It's got a floor, it's bounded below. Does that make sense to you?
Yes.
Now, what if both things happen? What if it's, look at this, every term of our sequence is never smaller than this, but never bigger than this. So basically, it's bounded above, it never raises above m. It's bounded below, never goes below little m. We just say it's bounded. This would be a bounded sequence.
It's sandwiched.
Yeah, that's right. It's got a ceiling and it's got a floor. It's like us right now. If I jump, I'm going to hit the ceiling. Well, my head's probably, I can't jump that high. I can jump. But I'm not going to go below the floor, right? I can't. I used to play volleyball. Anyway, I probably could hit my head on that ceiling.
Do it.
I'm not gonna do it. Maybe after the
run a
video's
little
off.
bit. Get a little run start.
Get a concussion. That'd make all-time views on YouTube.
That will get your views.
Teacher gets concussion teaching calculus too.
It'll be all over Facebook. And all.
Oh goodness, not going to do that. So anyway, we get this idea. If our sequence is always less than a certain number, it's bounded above. If our sequence is always greater than a certain number, it's bounded below. If our sequence is between two numbers, so basically if it's bounded above and it's bound below, it's bounded. That's the idea. Feel okay with that one?
Yeah.
Now here's the whole thing. We're going to put these two ideas together. Let's suppose that we have a monotonic sequence. This is going to be so logical. I hope it's logical to you. Let's say we have a monotonic sequence, and we know it's bounded. It's monotonic. That means what?
That it's either increasing or decreasing.
Always going up or always going down. And we know it's bounded. Always going up or always going down, and it's bounded. Tell me what's going to happen.
It's approaching a limit.
If it's approaching a limit, well, we'd say the limit exists. It's approaching, the limit exists as we're approaching infinity. Tell me something about the sequence.
Well, it's not mono decreasing or increasing.
Yes, it is.
It is, it's just bounded.
It'll stop at some point.
No, it won't stop.
What?
It's convergent.
What if it?
Ah,
Oh, see, we were right.
Should have been.
You should have been louder.
I want you to consider what would happen, okay? Look at this. Here's my bound above. Here's my bound below. My upper bound, my lower bound. Are you guys with me on this? Let's suppose that our sequence is bounded. Please watch up here while I'm doing this, okay? Suppose your sequence is bounded. Then your sequence is between here, correct?
Yeah.
This is not a monotone, this is a piece of crap. Okay? That's not nothing. That's doing nothing for us. But suppose that your sequence is monotonically increasing or decreasing. I don't care what it is. If it's increasing, I can start wherever I want, as long as it's in here, right? It's going to be increasing. Can I do, oh, no.
Nope.
Shoot. It's increasing, but it's bounded. But it's still increasing. But it's still bounded.
I'm still
But it's still increasing. Is it going to a certain number?
infinity.
What number it's going to?
M.
It's going to M.
And, oh,
The limit as n approaches infinity would be
and
big M. Does that make sense to you? Actually, we don't even care about this one because it's monotonically increasing. It doesn't even matter that it has a lower bound here. So I'll say a couple things. Every monotonically increasing sequence that's bounded above is going to converge. Every monotonically decreasing sequence that's bounded below is going to converge. Does that make sense to you? That's why this is here. If it's bounded, well, if you're monotonically, listen, if you're monotonically decreasing, you're going to be bound above at some point. At some point, because you're decreasing all the time, right? It's never going to come back up. So you can say it's fixed at that number, not an issue. Start with your first term. That's your bound above. What we care about for decreasing is the lower bound, don't we? Because we need to have a floor. We need to have this, the plane's falling, right? It's going to hit the ground eventually. It's bounded below. It can't keep going into the ground. Well, it's going to cause a crater a little bit. That's a horrible thought. You evil people, what are you doing putting thoughts in my mind? But it's going to be bound below at some point. If it's going to land, it's going to be bound below. It's going to eventually get to one level. That's what this is saying. If we have a monotonically decreasing sequence and we don't have this bound, we can't say anything about it. It's going to keep on going down. We don't know. But as soon as we say it's bounded below, as soon as we say that sequence is bounded, then we know it's going to be convergent. As soon as we say we have an increasing sequence and we say it's bounded above, of course this is terms, right? As soon as you know it's increasing, if there was no bound, we couldn't say anything about it. But as soon as we say, hey, it's monotonically increasing and there's an upper bound, it has to go to that number, big M. Show of hands if that makes sense to you. That's all I'm trying to say here. So that's the idea behind putting this together. Let me give you just one example to illustrate this. And talk about one more small idea and then we'll call it good for this section. Show that that sequence is convergent. Oh my gosh, how in the world can we show that that is convergent? Let's consider our sequence. Our sequence is 2 to the n, given by term, 2 to the n over n factorial. So far so good?
mm-hmm.
The first thing you might want to consider is whether this thing is,
monotonic.
yeah, whether it's increasing. Do you know whether it's increasing or decreasing? I don't know either. Well, you might want to plug in some numbers, huh? And find out whether it's increasing or decreasing. Might not want to just start taking a limit arbitrarily. So maybe find out whether it's going to fit this, whether it's increasing or decreasing, whether it's bounded above, whether it's bounded below. Let's deal with the increasing or decreasing first. So let's talk about that. 2 to the n over n factorial. Maybe we come up with the first like 5, 6 terms and figure out what's going on with this. So we do, first term would be 2 over 1 Yes?
Mhm.
Next term would be 2 to the second
4.
over,
2.
okay, well, look at that. Is that increasing or decreasing?
Same.
Neither. That's why for monotonically decreasing, we had the idea of less than or equal to, okay? So it can be equal to it for a while, but then it's got to start going down eventually. Does that make sense? Okay, let's do, this is 1, this is 2, this was 3, what is it? 8 over 6. Oh, something's happening. This would be 16 over,
24.
24, yeah.
I fell asleep a little bit. This would be 32 over 120. What's happening? Is this increasing or decreasing?
Decreasing.
We're going to look to try to show that this is decreasing. So if you don't know, Ralph, I don't know. I didn't know what that was. I mean, you got to look at it. I did because I did the problem before. Ha ha ha. But you'd have to think about it. What's happening here? This is staying the same, and then it's getting smaller and smaller and smaller and way smaller and smaller and smaller and smaller. So this thing right here says this is decreasing. However, does this prove that it's decreasing forever?
No.
We have not proved it. We've just done the first 5 terms. So we have this idea that we think it's decreasing. So it's decreasing? I don't know. We're going to think about it. We're going to see if it's decreasing. Now you got to show it. So here's what we're trying to show. I'm going to change this around just a little bit. So remember what decreasing means. Decreasing means that a sub n is greater than or equal to a sub n plus 1. That's what it means. It means that as we go term by term, we're getting smaller and smaller. Are you okay with a sub n plus 1?
Yes.
This means the next term. So we have, hey, term number 1, this would be term 2. Term number 7, this would be term 8. Term number 100, this would be 101. Does that make sense to you? The next term should be smaller. Now, I'm going to flip this around because I want to show you a certain way. So I'm going to flip this around. Another way you can think about it is that your next term should be less than or equal to your first term. It's just a little backwards. Do these things say the same thing to you?
Yes.
Okay. The reason why I'm doing this is because you can show this one of 2 ways. You can straight up just show it, like we did one example, or you can use a ratio approach. Watch this. If I divide both sides by a sub n, I would get a sub n plus 1 over a sub n is less than or equal to
1.
if you can show that, you show monotonically decreasing. If you can show this, you show monotonically. Does that make sense to you? Monotonically decreasing means this. That's what it means. This is the same thing as this. This is the same thing as this, provided one thing happens. Tell me something about a sub n for this to be true. It can't be, I don't care about 0, it can't be negative. Can't be negative. A sub n would have to be positive, otherwise your inequality would flip, because you'd be divided by negative. Does that make sense to you? So this will work if a sub n is positive. If a sub n is positive. So shall we try?
Sure.
I'm going to start from right here. So I'm going to do this one. So basically, we're going to work a little bit backwards. Let's start with the nth term. Right now, what we know is the nth term is this guy. It's 2 to the n over n factorial. You guys okay with that so far? 2 to the n over n. That's our nth term. The next term. Someone on the right-hand side, you guys, tell me what the next term would be. How would you find the next term?
2n plus 1 over
2 to the
Okay, hang on. 2n plus
no,
1.
2
Oh,
to
to
the
the
n
n.
plus
Okay,
1.
2 to the 2 to the
Freeze that, bro.
2 to the
N plus 1.
Power.
perfect. That's exactly right.
Yeah.
So look at
Freeze it.
if our first term is 2 to the n, our next term is 2 to the n plus 1 because we're dealing with positive integers here. We're just adding 1 to it. Does that make sense to you? So if our nth term goes 2 to the n, our next term starts out with 2 to the n plus 1. So far so good?
Mhm.
What's the denominator going to be?
N plus
N
1
plus 1
factorial.
factorial.
Perfect. How we show that is with those parentheses and then factorial. Quick show of hands, you feel okay with that so far? So this is the a sub n term. This is the a sub n plus 1 term. So far so good? If we're going to try to show what we thought, if we're going to try to show decreasing, so the reason why we did the first few terms, we go, well, I don't know what this thing's doing. Let's find the first few terms. The first few terms make it look like it's decreasing, right? That idea says, okay, if you're going to show decreasing, this has to be true. If you're going to show decreasing, this has to be true. If you're going to show decreasing, this has to be true, provided that's positive. So if we're going to show decreasing, this has to be true. Let's make the jump. Stick with me. If it's going to be monotonically decreasing, do you understand that this has to be true?
Yes.
Your second term must be less than your first term. That's decreasing. Your second term must be less than or equal to your first term. Your next term must be less than or equal to your previous term. That's all we're saying right here. Show of hands if you're okay with that so far. Now, what's kind of nice about this is that we can use the division of fractions as a complex fraction to solve this thing pretty nicely, pretty easily. So check it out. Is this always positive?
Yes.
2 then's positive, yeah? Is this always positive?
Yes.
For sure. So let's use this idea. Let's say, okay, well, now that we know that this is true, if we divide both sides by our a sub n, we get 2 to the n plus 1 over n plus 1 factorial all over 2 to the n over n factorial is less than or equal to 1. Now that looks nasty, but we're going to see a lot of this sort of stuff. Let's keep going with it. Firstly, show of hands if you feel okay getting from here to here. Show of hands if you feel okay with that. That's good. That's everybody. That's fantastic. Now, what do you do when you have a fraction divided by a fraction? You reciprocate this and you multiply. So this becomes n factorial over 2 to the n. So far, so good? Yes, no?
Yes.
I'm going to kind of move a little bit quick on this stuff, so stick with me here, folks. Now think about what this means. What this is, I hope you guys are with. If you get this, you're going to get the whole thing. Do you know that 2 to the n plus 1 is the same thing as 2 to the n times 2? Because this would be to the first power, you add exponents when you multiply common bases. This is n factorial. No? This is 2 to the n, no big deal with there. Here's less than or equal to 1. Now, here's the cool part. I want you to think about n plus 1 factorial. N plus 1 factorial would look like this. Please watch carefully. It'd be n plus 1 times n times n minus 1 times n minus 2 times forever until you get to 1. Does that make sense to you? This is n plus 1 factorial. That's what that is. Is that clear for you? You start with 11, then you do 10, 9, and 7, 6. Here's the cool thing about this. If this is n times n plus 1 factorial, what's this?
And factorial.
That's n factorial. Therefore, here's a little side note for you. You keep this in the back of your mind all the time. N plus 1 factorial is the same thing as n plus 1 times n factorial. Does that not make sense to you?
It does.
Hopefully it makes sense to you. N factorial times n plus 1 is n plus 1 factorial. This says, hey, you're taking n plus 1 times 1 less than that n times all the stuff before n. That's n plus 1 times n factorial. You guys okay with that one? Well, here's what's nice about that. Then this thing is n plus 1 times n factorial. Do you see anything that's going to simplify for us? Do you see why we did that? What simplifies?
N factorial.
Bam, gone. By the way, do you understand why we didn't just do a derivative here? Do you know how to do derivative n factorial?
No.
Okay. How about this one?
2 to the n.
What do we get?
2 over n plus 1.
Question. You need to now say whether this is true or false for n greater than or equal to 1. Is this true?
Yeah.
For n greater than or equal to 1?
Yeah.
Plug in 1, what do you get? You get 1. That's a true statement. Plug in 2, 3, and 4, and 5, and anything bigger than 1. Is this always going to be less than 1?
Yes.
Then this is true for n bigger than or equal to 1. Therefore, we've shown that this is always decreasing. We started with decreasing, didn't we? Look at the board, please. We started with decreasing, right? Hello, right?
Yes.
So we're decreasing. We showed that our work is all valid. This is always true for n bigger than or equal to 1. So therefore, this sequence is always decreasing for n greater than or equal to 1. If it's always decreasing, that's monotonically decreasing. You guys okay with that so far? Now let's consider what's going on here. So, 2 to the n over n factorial is, number 1, monotonically decreasing. Number 2, I want you to think of 2 to the n over n plus 1 factorial. Sorry, over n factorial. Tell me something about 2 to the n over n factorial. Tell me something. Think about what its smallest value could possibly be. Could it be negative?
No.
Okay, so right there you got it. If it can't be negative, what's the smallest value you could possibly attain or get close to?
0.
That means it's bounded below by 0. Does that make sense to you? It's got to be. You answered the question yourself. If it can't be negative, then this must be bounded below by 0. This is because a sub n is always positive. Now I'm going to make a little caveat here. This is bounded above by something. Okay, it's probably bounded above by where we start. So, are you with me? If you plug in 1, what did we get when we plugged in 1? We got, was it 2 or something? 2. Yeah. We got 2. So the upper bound is 2. Now, do I care about the upper bound right now? This function is always decreasing. Sorry, this sequence is always decreasing. Always decreasing. I care that it's decreasing. Do I care about the ceiling?
No.
Do I care about the floor?
Yes.
Yeah. So I care that it's decreasing and bounded below. I would care that it would be increasing and bounded above. It's not increasing though. It's decreasing. Is it decreasing and does it have a lower bound?
Yes.
Then what do you know about the sequence? Every bounded monotonic sequence is this bounded?
Yes.
Is it monotonic?
Yes.
Don't care whether it's monotonic, increasing or decreasing, if it's bounded appropriately. This is decreasing and bounded below. Therefore, this is convergent. Bam. Now you know if that made sense to you. You sure?
Yes.
Did you get the idea of what monotonically increasing is? What monotonically decreasing is? Do you understand that if it's increasing and bounded above, it's going to converge? Don't back up yet. I have one more minute to do stuff. I'm going to do it too. It's going to take 1 minute. So do you understand that it's bounded above and it's increasing, it's going to converge? If it's bounded below and it's decreasing, it's going to converge. So basically, if it's monotonically increasing, there will be a lower bound as well. That's why they use that word bounded. So it's bounded, increasing, no problem. Bounded, decreasing, no problem. That's the case we have here. The last little bit is just a little statement. It's a very kind of obvious statement. I want to give it to you before we end because it'll help you on some of this stuff. Little note. I want you to think of a number to a power of n. So, like, you give me a number. Give me a number.
1.
What? Say what?
1.
1. Okay, 1. Or 8. Or 1/3. And I say, okay, now take that number and take it to the first power. Then the second power. Then the third power. Then the fourth power. Then the fifth power. Then the sixth power. Then the seventh power. And every positive integer forever, okay? And I want you to look at what those numbers are doing. When are the numbers going to converge? When are the numbers going to diverge? You said 1. If you give me the number 1, it's going to be 1 forever, isn't it? That would converge. If you give me the number -1, it would be 1, -1, 1, -1, 1, or actually -1, 1, -1, 1, -1, 1, -1 forever. Would that converge or diverge? If you give me 8, give me 8. 8 to the first, 8 to the second, 8 to the third, 8 to the fourth. What's happening? Monotonically increasing without bound. Well, that's the whole thing, right? It's got to be bounded. That would diverge. How about 1/2?
Decreasing.
1/2 would be decreasing. It would also be positive. That would be bounded below. Monotonically decreasing and bounded below by 0. That would converge. You guys with me? About -1/2.
No.
No. Yeah?
John can look that up.
-1/2. Okay, this is going to be weird, but -1/2 to the n, same thing as -1 to the n times 1/2 to the n. Yes, no? Remember that whole idea that if the absolute value of the sequence converges, the sequence converges? Do you remember that whole idea about if the absolute value of the sequence converges, then the sequence converges? Booyah, converges. Okay. So here's the point. There's two numbers that are kind of our guidelines. 1 and -1. Anything between, do you understand that anything between there is going to get smaller? Fractions. Take fraction to a power, what happens? I don't care that it's negative. It's going to go positive, negative, positive, negative. It's going to, remember that whole thing? It's going to do this. Remember that?
Yeah.
It's going to do that if it's negative. If it's positive, it just does that. If it's a fraction. That's what that says. The reason why the -1 is not included is because the -1 we already did. -1 to the n goes -1, 1, -1, 1, -1, 1. It never gets any closer. 1's there because it's always going to be 1. Does that make sense to you? Okay. So, also, last thing, you can already tell what this is. If the limit's going to exist, what's it going to be?
0.
It's either going to be 0 or 1. Yeah, if it's monotonically decreasing, or it's the absolute value is going to tend towards one number, it's going to be 0 for r is not equal to 1. I'll say it this way. For r between those two numbers, it would equal 1 if r equals 1. That's the only two options you got. This is either going to go to 0 or it's going to go to 1. If this is 1, naturally it's going to be 1 to the whatever power is going to be 1. If it's not 1, it's either going to diverge if it's outside this range, or it's going to converge if it's inside that range. Have I made that make sense for you? Okay, question.